All right, let's get started again. So I want to talk about open-close principle next. So this was created by Bertrand Meyer, and he says that software modules, it could be classes, functions, components, whatever that is, should be, and the principle says should be open for extension, but closed from modification. So this looks like magic, right? How could something be open for extension but closed from modification? Well, when it comes to software, it's more expensive to change existing code, but it's often less expensive to add a little bit of new code that can work with other pieces of code. So the idea behind this is to minimize the change to existing code. If we want to change existing code, we got to first learn, understand how the code works. And then when we make a change to it also, we have the fear of breaking something that already exists. So we want to be able to add a little bit of piece of code and not rampantly change existing code. So that's basically the idea behind this. How can we minimize this? So for this, abstraction and polymorphism are the key in this case. So polymorphism and abstraction are the two key ingredients when it comes to keeping track of this particular principle and following it, or at least not violating it. Let's look at an example of this to see what that actually means. So let's say for a minute we have a class called engine, and in this case I'm going to simply take this engine class, and all I'm going to write here is a toString method. So, and I'm going to return a couple of things here. Let's say get class, and then following that I'm going to also return, let's say, hash code. Well, we know that the hash code, if they are same, then we can't say whether it's the same object. But if they are different, we know that it's a different object. So we'll just kind of go with that. So then I'm going to create a class called car. And in this case, the car class has a constructor. And all I'm going to do here is define two parameters, year and engine. So I've got these two parameters coming in. The year itself is going to be a field, so I'm going to create a field called year. I'm also going to take the engine as a second field, so that's going to be set here as an engine field, so that's good enough for now. Let's also go ahead and define a toString method just to kind of get a feel for what's in this car. So I'm going to say return, and here let's go ahead and return the year, plus let's say I want to return the engine itself in this case. So that's again enough for our purpose. So I want to first start with car. Let's say car1 equals new car 2016 comma new engine, and of course I want to output this particular engine, so car1. When I run this little code, you can see that it tells us that that's our car object. Well, good so far, but let's go a little further with this. What if I want to output, let's say, car2? Well, what is car2? Car2 equals new car, car1. Well, here I'm going to make a copy of the car. Well, you notice that it gives you an error, and the reason is Java doesn't have a copy constructor. Java doesn't have a copy constructor. C# doesn't have a copy constructor. Now you may wonder, why don't Java and C# not have a copy constructor? The answer is very simple. C# pretty much did what Java did, so there's no thinking over there. Well, what about Java though? Java said, well, C++ had a copy constructor, and that didn't go very well. So we're not going to do this, right? This is where you learn from other people's mistake, and how did they solve the problem? They said, copy constructor was a problem in C++, so in Java, no more copy constructor for you. That's called running away from real problem pattern. Well, that didn't really help. We can avoid it. What do? Well, you could use a clone method. If you think clone is a good idea, take a look at Effective Java book, and they tell you why clone is a terrible idea. We shouldn't use it. I won't go into the detail right now, but clone has its own problems. I'm going to write a copy constructor to solve this particular problem. So what am I going to do? I'm going to create a public, let's say in this case, a car, and I'm going to say other over here. And here I'm going to say year is equal to other.year. So great so far. Then I'm going to say engine equals other.engine. Well, we know that's not a good idea. You don't want the two cars to have the same engine. So it starts very naively and quietly, new engine, and I'm going to say create me a new copy of the engine. Well, immediately it gives you an error. Says you need a copy constructor for the engine. Okay, we can fix that. So I'm going to say public engine, and this is engine other. I don't have to do much here at all. But unfortunately, now you see this doesn't work because it also wants a regular constructor. So now what are you going to do? You're going to say public engine, and then you don't have to do much here also. Isn't that beautiful? You keep writing code where you don't have to do much. This is awesome language, isn't it? So we write all this code doing nothing, and the compiler is like, you're good, I'm very happy with you. So you're like, thank you, thank you, thank you. So that's basically what just happened is we've just worked for the compiler, we made the compiler happy. Now when we go back and run this now, what happens? Well, you can see that's a different hash code. So that's a proof that these two objects are different. If the hash code was same, we couldn't say it. Hey, but it's different. We are good right now. Well, we're done, right? So this code works. Let's say a few weeks goes by, and it's time for us to extend the software. So we are told to create a class called Turbo Engine, which extends from the engine. And of course, this is a turbo engine, so here's a constructor for the turbo engine, and here's a constructor for the copy constructor for the turbo engine. Isn't that beautiful? You write more code that does nothing. So now that we have written that, what are we going to do? Well, I can now come down here and I can say, well, this is going to become a turbo engine. Well, first question, will the compiler be happy now? The answer is yes, because a turbo engine is an engine. But when I run the code, unfortunately, though, notice how this is a turbo engine, but this is a very plain vanilla engine. We feel cheated, isn't it? It's like, hey, that one had a turbo engine. This one doesn't have an engine. So that becomes a problem in here, which is really ugly if you really think about it, right? So what do we do about this particular problem? How do we fix it? Well, one way to fix it is to think about what really caused the problem here. Well, unfortunately, what caused the problem here is that if you really look at this code, we are dancing around to solve one specific problem. Languages like C++, Java, and C#, new is not polymorphic. New is static binding, not dynamic binding. In a language like Ruby, new is polymorphic. You can actually call new on a class, and depending on which class you're working with, it can dispatch a new. You don't have that capability in Java and C# and C++ and a few other languages. So all we are doing here is to work around the deficiency of the language. So what am I going to do? I have a great idea here. I'm going to say if engine is an instance of, well, it's actually the other engine, isn't it, that we want. So we could say if the other dot engine is an instance of turbo engine, then I'm going to say engine is equal to turbo engine. And then, of course, in here, new, well, this is going to become new turbo engine. And then, of course, this is going to be turbo engine, other dot engine. And then, of course, if that is not the case, I'll say else I will do this. Now, if you notice, when I come back and execute the code, you can see that in this case, both of them are turbo engine. What do you think of this idea? Is it good? You're laughing. You should, yeah, thank you. At least I have one friend here, right? So absolutely, this is very good. You should have a positive attitude like he does, right? This is a good thing. Because what this code gives you is a wonderful job security. Because you could be sitting there and maintaining this code forever. But after a while, though, it becomes really frustrating. We don't like this job anymore, right? And so that's where it becomes problematic. This code is not going to extend because every time you add a new piece of, add a new class that extends engine, you got to come back and change this. And that's not going to be fun. So what are we going to do? We're going to rely on abstraction and polymorphism to solve it. So what I'm going to do is, I mentioned that the clone is not good in Java, and neither is it good in C#. How do I fix it? Well, I'm not going to use the clone built in Java or C# for that matter. I'm going to write my own method. So I'm going to create my own method, and the method I'll just call it copy. So I'm going to say public engine copy, and what does this do? It simply says return new, and I'm going to say engine this. And I'm going to make my constructor, copy constructor, protected. So in other words, we are bringing back polymorphism when it was lacking. So copy is polymorphic. So now I come to the turbo engine and I say copy method, but here I return new turbo engine this. And so I've implemented the copy method to return an engine. Then and of course, in the turbo engine, I'm going to make the copy constructor protected as well. So you cannot call the copy constructor directly from the outside, but you can call the copy method. So as a result, rather than going through this right here, what I'm going to do is I'm going to simply say engine is equal to other.engine dot copy, and I can make a copy of the object right here. Well, the beauty of this approach is when I run this code, you can see it's a turbo engine both ways, but I can also do one more thing. I can say this is piston engine, for example, where I can go back here and create a class called piston engine, where that extends from engine another time. And this, of course, has a copy constructor. It has a constructor, but it also has a copy method. And in this case, of course, it's going to return a new piston engine, and then this, of course. Now, the beauty of this is I did not change the car in any way, but when I run this code, you can see that in this particular case, it has a piston engine for both, so we don't have that extensibility issue anymore. This is something we got to keep in mind. How many times have you seen instance of in code with a series of if-else statements, right? When you have code like that, it becomes hard to extend it. Even worse, that code is duplicated in multiple times, and when you add a new type, you got to go change a lot of code. That becomes really a problem. But this is where we really want to rely upon abstraction and polymorphism. But we got to be very careful, though. If you start doing this for every single thing you do, you may actually end up with needless complexity. And there is no fun writing code with unnecessary complexity, because that's a burden you have to carry with you. So we got to be very careful. So the question is, we want the code to be extensible, but what is extensible? Well, that's the problem. I remember working on a project where the manager came to me and he said, my entire team every single day would tell me the software is extensible. This was like a mantra for the team. They would tell him, oh, don't worry, our software is extensible. Well, it so turned out on this project, they had extensible software throughout, and when they went into production, they found a little problem in production. The code was not doing something they wanted to do. So the manager told the company, oh, don't worry about it. We'll get you a change really quickly, like in the next day or so. When he came to the team and said, we should make this fix, the team said, oh, we need a few weeks to make the change. He was shocked. He said, why do you need a few weeks? And the team said, we got to change this, we got to change that, we got to change that, we got to change that, we got to change all of these things to accommodate it. So the manager came to me and he said, well, what does it mean when the team keeps telling me every day the software is extensible, but then when I tell them to change it, they want a lot of time? And I told him, it's your problem. You are at fault. He said, what did I do? And I told him the software is extensible until you asked it to be extended. If you didn't ask it to be extended, it will still be extensible, right? And this is our theory about extensibility. We plan for extensibility, and it's so extensible until you come to me and say extend it. I'm like, oh, I can't do this now. So how do you really make a software extensible? There are two things you need. Knowledge of domain. I can't tell you how many times developers underestimate it. If you don't know the domain, how could you make something extensible? You're just talking theory at this point. I used to work in companies where I would go to the domain experts and say, should we handle it? And they would tell me, if you ever do this, you'll violate the law of physics. Oh boy, why would I want to do that, right? Well, I don't know the domain. I'm trying to understand the domain and implement it. I should have the courage and the ability to go ask them these questions. You also need the knowledge of software design as well. And if you don't understand software design, what happens? At times people come to you and say, make this change, and you say, oh boy, that's going to be a lot of work to make this change. And they will say, well, what does it mean by software? It's very soft, right? You should be able to make a change to it. And then you try to tell them, no, software doesn't mean that we can do anything you want anytime you want to. We got to design for it. And they look at you like, why would you have to design for it? It's a software, right? So we need to understand design concerns as well. But here comes the problem. There are three kinds of people that you work with. And this is in every project. There are three kinds of people you work with. The first kind, know domain well, know nothing about software. These people have taken a Fortran course back in school, and they are software experts now. But the point is, they don't understand the software constraints. They know the domain extremely well. Then there is the second group of people. Know software design well, but what about these people? Well, know nothing about the domain. So these people, a lot of us are like that, right? We know software, we don't know much about the domain. There's a third group of people. Know software and domain really well. You know who these people are in your company. If they're in a room, you turn off the light, you will see a glow, right? These people glow and you know, oh, there's the person who knows that. We'll politely ignore the fourth category. We won't talk about them here. Well, the point really is, these are the three groups we have in companies, right? But who do you think can really make these decisions well? I'm going to say it is a third category, because they understand software really well, they know the domain really well, they can balance things out. But the reality is, they are busy glowing in the dark. There's not that many people in the companies like this. So that really amounts to these two people that we have to deal with. Folks who understand software, folks who understand domain, you got to bring them together and they got to talk to each other. If they don't talk to each other and they stay in different floors, oh, by the way, they used to stay in different floors, but that was in the previous century. Now they stay in different countries, because that worked so well in the past, right? So a company said, this is awesome, we'll put them in different continents. Well, next thing you know, they're going to be in another planet, right? Because we have tried other countries and that really didn't work. Let's send them to another planet. And we call this agile somehow. Okay, so the point really is that we really have to interact with these people more for us to be able to figure out these concerns. Otherwise, we simply cannot plan for extensibility. That's pretty difficult to do in general. So we want to really plan for extensibility. Abstraction and polymorphism are very important, but we don't want to arbitrarily plan for extensibility. It's got to be really based on real purpose and real demand. Otherwise, we're going to create unnecessary complexity, and we don't definitely want to do that. Well, the next principle I'm going to talk about is called Liskov substitution principle. And this principle is all about inheritance. So Barbara Liskov wrote this principle, and she said, inheritance must be used. So inheritance should be used only for substitutability. So substitutability is the key when it comes to inheritance. So in other words, don't use inheritance for code reuse, use it for substitutability. So what does it really mean? What it really means is, if an object of B may be used anywhere, an object of A can be used, then use inheritance. If an object of B should use an object of A, then use delegation. So in other words, use inheritance only when you want substitutability. If all you want is code reuse, then don't use inheritance. I'm going to say inheritance is one of the most misused concepts in object-oriented programming. And we tend to really suffer through the consequences of it. So avoid using inheritance unless you really want substitutability. Well, let's think about this a little bit. I'm a why kind of a guy, so immediate question is, why? Why shouldn't I use it? Well, the reason is implementing a derived class is a burden on the programmer. So you have to take on a lot more effort to implement inheritance than if you just use another object. But why so? Because every service of the derived class must be, so in other words, the external behavior of the derived class must be consistent with the external behavior of the base class. So what that really means is, every service of the derived class should require no more and promise no less than the corresponding services of the base class. So this is a burden we have to carry with us. So every service of the derived class should require no more and promise no less than the corresponding service of the base class. You can ask the question, why again? And the reason is, she kind of nails it down here. She says, because the user of the base class should be able to use any of the derived classes without knowing the difference. So in other words, if you violate LSP, the user of your class will violate open closed principle. So that's really what it comes down to. If you violate Liskov's substitution principle and you use inheritance when it is not the right choice, the users of your code would have to violate the open closed principle. They are going to start deciding what kind of object they are actually using. Let's take an example for a minute. Let's say I have a class, a base class, and I'm going to throw an exception for a certain problem. You are the user of my class. What are you going to do? You're going to call methods on it, and you're going to put exception handling around it and say, I'm ready to handle it. Well, tomorrow, somebody comes and inherits from my class, but they decide to throw a different kind of exception. Well, somebody takes your object and that object and passes to your function. What does your function do? Waits eagerly for this exception or a right result. But suddenly the code throws an exception totally unexpected. And your code says, wheeze, like, whoa, I've never seen that one before. Where did that come from? And your code suddenly fails. You're not going to be able to handle this. And what do you then do? Somebody files a bug. They always blame you for the bugs. So what are you going to do? You're going to say, if the object is base type, do this. If it's a derived type, do this. Because you have no other control over this. And you end up violating the open closed principle doing this. So I'm going to give you a few examples of this. So where do we see this? I'm going to give you good examples first. So a first good example. A method is public in the base class. So let's talk about Java. Let's talk about C#. Let's talk about C++. So first question for you in Java. Java programmers in the room. Anybody? Oh, awesome. I'm in the right place. So question, can the method be protected or private in the derived class? What do you think? No, the answer is no, right? It cannot be. It can only be public, right? That's correct. Okay, well, another question. A method is protected in the base class. What can it be in the derived class, Java? It's protected or public, right? Awesome. What about C#? A method is public in the base class. Can it be protected or private in the derived class? In C#? Any C# programmers in the room? All right, don't be shy. No, the answer is no. If the method is protected in the base class, can I make it public in the derived? No, you can't, because C# is special, right? So they're like, public is public, protected is protected, and then of course private is, private is private, right? That's the rule of C#. In Java, you can be the same or lenient. In C#, it's got to be exactly the same. Any C++ programmers in the room? The two Ukraine C++ programmers are in the room today. Awesome, right? So C++, if the method is public, private, protected, what can it be in the derived class? Come on, don't be shy. Anything you want it to be. This is total freedom, isn't it? There's another name for it, anarchy, right? So why is this? Because C++ is pure wilderness. It's like a jungle. There's no rules. You can do anything you want to do, right? Well, this is the idea behind how languages kind of try to embrace this. And C++ says, don't worry about it. Programmers are smart. They'll figure it out. Well, Java and C# are like, let's follow the Liskov substitution principle. So they restrict you from what you can do. So you can see the differences between the languages. This is one example. Another example, let's say we have a base class throws E1 as an exception. Java can, that method in the derived throw, let's say throw exception E2. What do you think? Or was it? No, unless E2 extends E1, right? Even there, I would argue it's a violation of LSP. The compiler doesn't stop you, but you could be extending from that and throw for no other reason than arbitrary ones, and it would still violate. C#, what do you think? Yes or no? No rules here, right? Because C# wants to be like C++ in this case. Like, I can do anything I want. So it doesn't really stop you in this case. And so there's no, excuse me. I talk about C++ and I get sneezing. Okay, all right. And of course, you know the answer for C++. I wouldn't make fun of it again. All right. So that's good examples. Bad example. So where this has gone really wrong, let's take a look at an example here. Let's take a look at the class which is stack. So what about stack? Let's take a look at the stack. And let's go to the stack class and take a look at that for a minute. Look at what stack is doing. Stack extends vector. Wait a minute. Do you remember what a vector is? A vector says you can insert elements anywhere you want to. You can remove elements from wherever you want to. And you can put stuff, remove stuff, all those good stuff. What does a stack say? A stack says I'm a LIFO. Last in, first out, right? So you can put things on the top, you can remove things from the top. Well, imagine for a minute, he has a function that takes a vector. And what does he do with this function? In the function, he is given a vector, he inserts elements anywhere he wants to, removes elements where he wants to. Well, he has a function that takes a vector, and what does he do? He calls this function. And he says, give me a vector, I'll take it and forward it. Well, I come along, take a vector, give it to him, he sends the vector to him, everything works fine. Now I take a stack on my hand and I pass it to him. What does he say? Nice vector. And passes it down to him. What does he do? He removes elements and puts elements anywhere he wants to. Then I get the stack back. Hey stack, how are you doing? And the stack says, don't ever do this to me again, right? Because the stack feels totally violated. It's like, it limps over to me and says, please, he did bad things to me. Well, he says, what did I do? I just got a vector. I treated it like a vector. He feels really bad. It's okay. You didn't know this, right? So you just got a vector. You're dealing with it. But poor stack says, I don't like the way I was treated over there. Well, we totally violated the invariant of a stack, right? That's the problem here. We treated the track poorly because we violated the invariant of a stack. So this is where the problem comes in. We really have to ask the question, you know, is a stack, can I use a stack anywhere a vector is being used? And the answer is no. Our goal may be to reuse a vector in the implementation of a stack, but not to be used as a vector. And that's where the difference really comes in. So, given that, let's talk about this a little bit further. Now, if you're working on a code, Java or C++ or C#, whatever it is, now we all can agree, oh, we don't want to use inheritance unless it really means substitutability. A noble thought, no doubt about it. But what happens in reality, however? In reality, though, when we are working with the code, other temptations often kick in. Let's look at an example here. Let's say for a minute, we have a class called A, and this has a function public void f1. It also has a function, let's say f2. And in this case, it doesn't really matter what these functions do. But we are told, write a class, let's say write a class B with methods let's say F1, F2, same as in A, and F3. So I can say class B, and I can write the method public void F3 here. But wait a minute, I need to implement F1 and F2. It looks very tempting right now because I can do the least work, extends A. Look how cool that was, right? Very fast to write it. But wait a minute, did you really mean that B can be used anywhere A can be used? No, I didn't mean that. Well, then that's what you bought into, whether you liked it or not. An alternate solution would be to go back here and say public void F1, and here you can say object.f1, and then you can also say, for example, public void int F2, and then you could say return object.f2, but of course, what in the world is obj? A object equals new A. But notice how you had to type all of that manually here. How do you solve that problem? Well, you can find somebody who's really fast in typing. So they can type it in no time. Maybe this person goes around the office. Do you want me to type something today? Right? So you make use of them. Typing as a service. Hey, there's a business for you. Or we could simply say, this is so common problem. In fact, there are IDEs that say refactor, and it's so common, they even give you that little thing, replace inheritance with delegation. And you can select it, and before you can blink your eyes, you can click on a button, and they vomit that code for you. So you could use tools like this also. But nevertheless, there is an issue right now. And the issue is, whether you type this manually or used a code generator to do it, keep in mind that code is in front of you. And there's a consequence to it. And the consequence is this. LSP, so let's say in Java and C#, don't violate LSP. Okay, great idea. But what's the consequence of that? Now you are violating OCP and dry. How so? Notice now, you have duplicated the effort here. It's not duplication of code, but duplication of effort. For the methods in A, you have to write methods in B. That's a violation of the dry principle. Secondly, if somebody comes along and changes a signature of a function in A, this is going to be blown out of water. You got to come back and rechange this. That's a violation of open-closed principle. Change to one piece of code affects another piece of existing code. It's a violation of OCP and dry. Well, then the question is, now what? Well, my answer is, if you have a choice, you would rather violate LSP. You would rather honor LSP. Why? Because if you violate LSP, the user of your code will violate open-closed principle. Here, I violate open-closed principle, but my user doesn't have to. I would rather create a bad design for myself and look honorable for my users. On the other hand, if I violate LSP, they have to violate OCP. Now we got a double jeopardy, right? But ideally, it would be nice if we don't have to violate any principle at all. How do we do that? Well, short answer, if you're using Java, you could use Project Lombok, and that can give you this feature. But I'm going to show you this feature in Groovy rather than in Java. So let's look at Groovy for a minute. Class worker. So here is a class worker. Define work. And just to make sure this is working, we'll just say working. And I'm going to say new worker.work. Let's make sure that code is compiling and running. Awesome, that's working. Now you have a class called worker. Now I create a class called manager. As you would expect, the manager does absolutely nothing. And in this case, of course, I'm going to say define Bob equals new manager. Then I call bob.work. This is an alien concept for a manager. You're calling a work, but this manager is very smart. This manager says, I can handle it. But how can this manager handle it? Well, the reason is, I'm going to go back here and say delegate, and then I'm going to say worker, and this is going to be victim equals new worker. And now when you run this code, you can see how that actually does it. So this is an example of where we're not violating LSP. You cannot send a manager where a worker is expected. You are doing a code generation at compile time. You're not violating the dry principle. You're not violating the principle of open-close principle also. So this is much better. You can do the same thing, by the way, if you're using Project Lombok in Java, you can do that too. And if you're using C#, you can use Java and you can use this too. So the point really is that you can use some of these tools to get around these problems, and you can, avoid these kinds of issues. And that's basically what LSP kind of gives you. The last thing I want to talk about is the dependency inversion principle. But I'm going to talk about dependency inversion principle even without writing a single line of code. Well, anytime you have used, automated testing, you have used test doubles like stubs and mocks, chances are you have used dependency inversion principle. So what does this principle say? It says a concrete class should not depend on another concrete class. Both should depend on an interface or abstraction. Before I go further, I want to emphasize, don't take this literally and do this every single time. Because if you do this blindly, you get complexity in your code. So these are principles, and you have to really say, does it make sense to do this right now? Otherwise, we put on this blinder and do this all the time. Then we got a very bloated system that we have to work with, and nobody wants to work in such a system anyways. So the point is, these are just principles, and we got to decide, does it make sense in this context, and then apply it. But having said that, let me give you an example of this principle. But I'm going to give you an example of this principle without really writing a code. But here is poor little concrete Venkat. And here's a clock. So this was my experience several years ago. So this was, I go to Norway very often these days. I'm there, almost continuously every few weeks. But my first trip to Norway was in 2001, and I fondly remember that time. Remember 2001, I know it's hard to remember, but 2001 was the time before, we have the cell phones. And laptops were just, kind of getting popular at the time. No smartphones, no cell phones, the way that we know. And so I land in Norway, check into this hotel on a Sunday afternoon, and I looked around and I was kind of a little unhappy because there was no coffee machine in this particular hotel room. And I'm a person who has to drink coffee all the time. And there was no coffee machine, so I got really frustrated. I went to the reception and said, there's no coffee machine. And she said, no, we don't give coffee machines. I argued with her enough to eventually get a coffee machine. She's like, take mine, so, have it. So I was getting ready to go to bed. I normally don't have jet lags. I travel a lot, so I go to bed early. I'm one of those old guys who go to bed early and wake up early. So I was getting ready to go to bed. And I looked around the room, and I was in a state of panic. Because in the hotel room, there was no clock. And I said, what's the matter with these hotels? They don't give you anything maybe that starts with a C. No coffee machine, no clock. So I went to the reception. The lady was still there. She kind of rolled her eyes and said, here comes the trouble again. And she said, what do you want now? I said, well, I don't have a clock in the room that bothers me. She said, why do you need a clock? I said, because, in the morning, I got a clock by my bedside at my home. It makes such a horrible noise, I cannot sleep for the rest of the day. I want a clock to wake me up. She looked very confused. She said, what you need is not a clock. I guess what you need is an alarm. I said, lady, don't get technical on me. Well, she said, but you need an alarm, not a clock. And she was right. And then I said, okay, fine. I think I need an alarm. But I looked in my room. I didn't see a clock. She said, you don't need a clock. Well, fine. I didn't see an alarm. She said, did you turn on the TV? I said, no, I don't watch TV. Well, this week you will. So I went back to the room and I turned on the TV. And what a surprise, the TV was an alarm too. This is, once in a while you got to turn on TVs, I guess, to figure this out. Well, I set I'm a big fan of TDD. I'm not going to assume things work. So I set the alarm in the TV for about a minute away, turned off the TV. And what a surprise, a minute later it turned on. But I was curious. I want to make sure it's repeatable, right? So I set it for 2 more minutes, turned it off, and 2 minutes later, guess what? It turned on. But I noticed something a little weird. I changed the channel, don't ask me why. I changed the channel and I turned it off, but it always turned back on CNN. I thought this was kind of weird. But anyway, I went to bed. Now you should imagine my plight. Just imagine this. I'm in a dark room, sleeping wonderfully because I don't have jet lags. Suddenly, I hear voices in my room. In a panic, I jump out of my bed. First, I don't remember where I am. And I hear this voice, and in front of me, the scariest picture ever you can wake up to. Right in front of me is a guy in suspenders. Hello, this is Larry King Live. Can you imagine waking up to Larry King Live in the morning? I had to go into counseling when I went back home. So now that I was awake, I started thinking about what this lady taught me, and she taught me a really important lesson. I got to tie this back in. So what did she say? She said, well, you concrete Venkat should not depend on concrete clock. You should depend on an alarm. What a great idea. What did that tell me? It told me that TV could be an alarm. This is one place where you would have ever seen UML diagram being done in Notepad. Okay, there we go. So what am I doing here? I've got this TV on my hand, and this TV, of course, is going to be an implementation of this alarm, as you can see right here. But of course, you think I'm going to do that next day. No, I wrote a little program on my computer, which is going to be the alarm for the rest of my trip. And so my computer could be an alarm. Well, these days, my smartphone is an alarm, and I can use the smartphone to remind me. I could have, not that line, and of course, I can have any number of other solutions. But look at the beauty of this. Rather than a concrete class depending on a concrete class, both the concrete classes now depend on an abstraction. And that's exactly what the dependency inversion principle says. Rather than a concrete depending on a concrete, let the concretes depend on an interface so your code becomes a lot more extensible. And we have used dependency inversion principle a lot. In a way, I see this as good cop and bad cop. You're trying to avoid violating open-close principle, and you're often trying to implement dependency inversion principle in your code. So what I did here in this presentation is I talked about a few different principles. Sometimes people use the word solid principle for these, but I'm not a big fan of some of these acronyms. But solid stands for single responsibility principle, open-closed principle, Liskov substitution principle, and dependency inversion principle. I didn't quite talk about the I in solid. It stands for interface segregation principle, which is just cohesion at the interface level. But the reason I'm not hung up on solid is we did talk about the dry principle and the Yagni principle as well. And I believe firmly that these two principles are as important, if not more, than these other principles. If you are deeply into acronyms, maybe you can call them as disold principle if you want to call it. But the point really is that I don't want to just say only solid principles. I really care about these other principles as well. And I found these principles to be invaluable in what I do. Not only do I use these principles, but these principles have become vocabularies among the teams that I work with. So when I work with developers, rather than telling them the code is not good, change it, I can simply tell them, hey, we are violating dry over here, let's keep it dry. Or let's follow OCP here. Or let's apply dependency inversion principle here. It becomes a nice vocabulary to communicate. And as a result, it becomes a lot more educated team where we are thinking of principles. Similarly, when the team is working on design solutions, we often try to identify the design principle behind a particular problem. Then when we look for design patterns, we ask the question, does these patterns, what are the principles behind them? For example, if you look at abstract factories, what is the design principle behind abstract factory? It's open-close principle. Hey, what about composite pattern? Well, the real principle behind the composite pattern is Liskov substitution principle. Hey, what about strategy pattern? The design principle behind strategy pattern is dependency inversion principle. This opens up door for looking at the world very differently. You don't see patterns as patterns anymore. You try to see what design principle is behind a pattern, and then you see if there's a match behind it, and you can use it. If you're interested in the code examples or these contents, you can download from my website. I hope you found that useful. That's all I have. Thank you.